This is Lab 4 Oscillations. Introduction. The purpose of this oscillations lab is to create or use a given video of a hanging spring mass system to evaluate the position of the mass on the spring. I first tracked its position in Tracker, then created a code in GlowScript that graphs the experiment data versus the model's prediction. The fundamental physics in this lab are conservation of energy, Hooke's law, Newton's second law, and oscillatory motion and periods. The results of me tracking the mass were very close to the model's predicted position. The energy graph predicted the total mechanical energy to be constant. The main physics equations in this lab were the net force, which is the mass times dv over dt, the force of gravity, which is negative mg, the force of the spring, which is negative k times the stretch times L, the kinetic energy, which is 1/2 mv squared, gravitational potential energy, which is mgh or mgy, the the spring potential energy, which is 1/2 k times the stretch squared, and the total mechanical energy, which is kinetic plus potential of the spring and gravity. The experiment. The system is a mass spring system with an external force is Earth's gravity. The axes were positioned where the spring connected with the wall. And here's the video. On the right, you can see the X position and Y position versus time, and on the left, you see the video of the mass moving. The code. So my mass started at negative 0.132 in the X direction and positive 0.622 in the Y direction. The spring constant was 6.83. The initial unstretched length of the spring was 0.123 meters, and I computed the initial energies, K, gravity, potential, and spring potential. I began at t equals 0 seconds and ended at t equals 9.972 seconds. The ball mass was 0.402, and the delta t was 1/210. As you can see on the picture on the left, I computed the initial energies with those equations that I mentioned earlier. And then inside the loop in the right picture is calculating the net force and updating that, and then computing the final energies and updating those and plotting them. The results. So I imported a CSV file of the X and Y positions of the mass, and I outputted an X position and Y position versus time graph, and then an all energy versus time graph, and a model of it, which is on the right. The change in energy versus time graph, you can see the energy, which is the orange line, the total mechanical energy, stays constant throughout, and the Y and X positions are very close to the modeled prediction. The experimental data and model shows similar motion. The mass swings in an arc while oscillating vertically and horizontally, which is consistent with Newton's second law and Hooke's law. The oscillation periods in X and Y are close between data and the model, though small differences in amplitude or phase occur due to air resistance and errors in collecting the data. Energy plots from the model show nearly constant total energy, while the experimental data may lose energy slightly, reflecting non-conservative effects or errors in collecting the data. What does it mean? So for the first question, for your model system, is the energy principle satisfied? Well, it is satisfied because based on the graph, the total mechanical energy stays roughly constant. And then the second question was, using the data you obtained in Tracker, make two separate estimates of oscillation periods. The first one is the X position and the second one is the Y position. So the two estimates are about the same because I divided the total time by the number of oscillations, which is about 6 oscillations for both the X and Y components. And so the total time, which is 9 point something, divided by 6 is about 1.58 seconds. Sources of error. I didn't perfectly track the mass at each frame, which could lead to imperfect positions. And I didn't place the axes and measurements in Tracker in the exact correct places, which would have messed up the data values. And then there was also air resistance and possibly friction between the spring and the mass and what was holding it, which was not talked about or implemented into the lab. Thanks for watching.